Hello students, in this lecture we are going to see how to evaluate Fourier transforms for simple functions. In last few classes we had introduction to Fourier transforms and we learned some properties of them. So in this class also let us see how to evaluate the transform for simple functions. So take the first problem here. Evaluate the Fourier transform of the following rectangular pulse. So this is the rectangular pulse they have given, and hence to deduce two integrations. So first let us see how to evaluate the Fourier transform for this rectangular pulse, then later we shall go to these deductions. If you see this rectangular pulse, first mathematically let us write the expression for f of t. If you see this f of t function, this is t axis and this is f of t. For t between minus t to capital T here, or capital T may be the time period. So from minus capital T to plus capital T, what is the value of the function? F of t is having the value 1 if you see here. So f of t is having the value 1 between the values minus t to plus t. So that's what is written here. F of t is having the value 1 from minus t to plus t. In other intervals, that is after minus t to this side left side and after plus t to the right side, if you observe, the function is taking the value 0. The function is taking the value 0. So f of t is going to be 0 between this side and the other side. So this is how the function f of t is defined. The function f of t is 1 from minus t to plus t and 0 in other sides. So 0 otherwise we have written. So for this f of t, this is the rectangular pulse we have represented. For this function, we need to find the Fourier transform first. So Fourier transform definition is given as capital F of x equal to 1 by root 2 pi minus infinity to infinity f of x e power isx dx. This is the basic definition of Fourier transform for any given function f of x. Since here the function is represented as time function t, let us rewrite this formula using the variable t. So instead of x, now let us write using t, just the name change. Instead of x we have used t here. Now look at this f of t. Let us substitute f of t from here. The f of t value is 1, but it is not for all the intervals. When for all the values it is having the value 1 only from minus t to plus t. So this integration also for the values of small t lying between minus t to plus t, from minus t to plus t, the function is having the value 1 into e power ist dt. Otherwise, it's going to be 0. So the integration minus infinity to infinity will be only from minus t to t. And from minus t to t, the value of the function f of t is 1 into e power ist dt. Now look at this e power ist, which can be written as cos plus I sin. E power I theta, we know the basic formula, cos theta plus I sin theta. So using that we have written as cos st plus I sin st. And now when you observe this, cos is an even function because we know cos of minus theta is cos theta itself. Sin of minus theta will be minus sin theta. So sin will be odd function. So this is even function and this is odd function. Why we need to consider these as even and odd? Now why we need to discuss about even and odd here? Because since the integral is minus t to t, we can make use of the basic formula. When you have minus L to L, when you integrate an odd function, the answer will be 0. And when you integrate an even function from minus L to L, it can be written as 2 times the same function from 0 to L. So this is the basic integral formula for odd and even functions from minus L to L when you integrate an odd function, because odd function means f of x will be equal to f of minus f of minus x in the negative interval. Even function means f of x will be equal to plus f of minus x in the negative interval. So that's why it will be 2 times 0 to L. So using this concept, you will have the second integral becomes 0 and the first integral can be written as minus t to t can be written as 2 times 0 to t cos st dt. Since the even function will come as 2 times 0 to t and the odd integral, second integral will become 0 according to this concept. So now this is the only term we have. Now let us see how to integrate this. So f of t is going to be 2 by root 2 pi. Cos, when we integrate, we have sin ax. So sin cos st, when we integrate sin st divided by s, because the integration is with respect to t. So with respect to t, when you integrate, s is going to be constant. So by s will come integral 0 to t. So 0 to t. Now we have to apply the limit. What is the upper limit? In the place of t, I have to put t, capital T here. So sin s capital T by s. This is the upper limit minus lower limit. What is the lower limit? In the place of t, I have to put 0. So sin 0, 0. So lower limit will be 0 here. So it is root of 2 by pi, because this root 2 and 2, this 2 can be written as root 2 into root 2. So 1 root 2 can be cancelled. Root of 2 by pi sin st by s. So this is the final answer of the Fourier transform, which can be written as capital F of s. So if you observe, when you take Fourier transform of your function of t, the final answer you will get in terms of s. So here we get a final answer as in terms of s, capital F of s. So this is a Fourier transform. Now let us go to the deductions. They have asked to deduce two integrations. So let us start the first integral. Integral 0 to infinity sin t by t dt pi by 2. This deduction. Now look at this integration and look at the answer, because from the answer we need to deduce this. So look at this integral and look at the answer of Fourier transform. Are we not having the same term? Yeah, very similar. The exact term is sitting here. Instead of the variable s, here we have the variable t. But of course the same similar term is there. So let us use inversion formula. So when you have similar term to the answer, you have to go to inversion. So let us use the inversion formula. This is the inversion formula of Fourier transform we have written. Now in the inversion formula, change the variable x as t, because since we are dealing with the function of t here, f of t equal to 1 by root 2 pi minus infinity to infinity. What is f of s? See, here we got the answer of f of s like this. So substitute this f of s here into e power minus is t ds. See, in the place of x we have written t, just the name change of the variable. This capital F of s is this answer we have substituted. So that is why we get this term. Now in order to get the exact integral, we need to do certain manipulations here. So if you look at this term and the integration, see here after sin t by t we do not have any e power term here, but here we have an e power term. So this should not come. So let us substitute this t as 0. So when we substitute t 0, this will become e power 0 1. So that this term will get vanished. Similarly, this capital T, when you look at the sin t only here we have, but here we have sin s into capital T. So this capital T, which is the time period, we can make as 1. So when you do these two adjustments, that is small t 0 and capital T 1, this becomes f of 0 equal to 1 by root 2 pi minus infinity to infinity root of 2 by pi sin s by s e power 0 ds. And what is f of 0? Function is defined as 1 in minus t to t. So f of 0 will be, when t is 0, f of 0 will be 1. So here f of 0 is 1 and e power 0 1. So substitute these two values here, you get. And since one more manipulation we need to do. See, when this e power 0 has become 1, in the integral, this root of 2 by pi we can take out. In the integral you will have only sin s by s. And when you observe, sin s by s will be an even function, because sin will be odd function and s also will be odd, because when you substitute s as minus s, here minus will come, here also one minus will come. So this minus and this minus will be cancelled and totally this will be a even function. So since this is even function, this minus infinity to infinity we can write as 2 times 0 to infinity. So that is what we have written here. So here we have 1 by root 2 pi. This root of 2 by pi has come out. This minus infinity to infinity we have written as 2 times 0 to infinity. And changing the variable s to t. Changing the variable of integration as s to t. This becomes sin s by s becomes sin t by t. And ds becomes dt. Here. So from here, cancelling out the terms, you will get easily integral 0 to infinity sin t by t dt as pi by 2. So this is how we reached the first deduction. Now let us go to the second deduction. Integral 0 to infinity sin t by t square dt pi by 2. So the difference here is, in the first deduction we had sin t by t. In the second deduction we have sin t by t whole square. Now when you have this whole squared, from the Fourier transform answer directly we may not be able to get. For instance, if you look at the Fourier transform answer, here you have sin s by s, but in the deduction we have square term. So when we need to square the answer, we have to go to Parseval's identity. So this is the Parseval's identity which we had learnt already in the first lecture. So here only you have Fourier transform square itself. So that is why we are coming to Parseval's identity. Now before going to Parseval's identity, let us write what is the small f of t and what is capital F of s. So small f of t is the given function which is 1 from minus t to t, and capital F of s is the answer, Fourier transform answer. So from here you take and write the answer here, capital F of s. So this is f of t and this is f of s. Just substitute both sides. So what is left hand side? Capital F of s square, modulus square. But here, since the function is a real function, there is no complex term here. It is just mere squaring. So square capital F of s into ds. Right hand side is squaring f of t. So what is f of t? 1. So 1 square integral dt. But there is a restriction for f of t. The limit is not minus infinity to infinity. F of t is defined only from minus t to t. So this is going to be just minus t to t. So left side you have, now substitute in the Parseval's identity. In the left side what you have? Integral mod f of s square ds. So this is the term, left side term, and this is the right side term. This is the right side term. So let us equate. So equating both sides, this is the left side and this is the right side. So this is the left side which is equal to this is right side. Now when you look at the right side, minus t to t, 1 squared is just 1. So it is dt. Now this is a very simple integration. We can integrate and get the answer. Integral dt is t from minus t to t. Apply the limit, upper limit minus lower limit, t minus minus t. So the final answer is t plus t 2t. So we have got the answer of the right side, this right side integration as 2 into t. Now look at this left side. Small manipulations we may have to do. See, sin s by s is going to be an even function, and let us put this capital T as 1. So capital T, let us put the value as 1. So when you do that, so this will become capital T 1 and this is even function. So we can write this 2 into 0 to infinity and changing the variable, because in the question they are asking in terms of t, but here in this integration we have in terms of s. So let us change the variable of integration s to t. Changing the variable of integration s to t, and value of t we can substitute as 1. And since the integrand is an even function, using all these concepts, this left side integral now becomes, this minus infinity to infinity now becomes 2 times 0 to infinity, and this root of 2 by pi, when you square it becomes 2 by pi here, and sin st by s. So this capital T we have substituted 1. This s has become t now. So this is sin t by t whole square dt. And the right side, what we had in right side, this is right hand side, we had 2t. Of course, since we are putting t as 1, the answer is 2. So this is how we get, this is the answer. Now just simplifying this, cancelling 1, 2 and 2 will be cancelled both sides. The answer of this integral is going to be pi by 2. So we have got the second deduction also. So in this lecture we had seen how to evaluate a Fourier transform for a rectangular pulse. We evaluated Fourier transform using the definition of Fourier transform. We got the answer as this, and using this answer we deducted 2 integrations. The first is this and the second deduction is this. So using the concepts whatever you have learnt, try out these problems. So the first is again you have to evaluate Fourier transform. Here frequency response means it represents Fourier transform only. Thank you.